So now let's switch to 3D. And I mean, 3D is much more complex, but that is what the game we have now is that once we have seen what is the way, the ingredients of the 1D theory, extension to 3D is just using the same ingredients. And that's my goal here. So I'm not intending to make you acquainted with all details of the mathematical theory of incremental 3D plasticity, which is a little complex, but rather to see that the ingredients are the same. Okay? There are some unloading, some additional ingredients, but we'll talk about that at the right moment. So, first ingredient, the additive decomposition of a strain. We remember in 1D, we decompose the strain into the elastic part and the plastic part, where the elastic is defined as the one following the standard Young modulus, the standard elastic constitutive law. So the strain is equal to the stress divided by the Young modulus. Okay, we do the same in 3D. The 3D, the 6 different components of the elastic of the strain in 3D are decomposed in one tensor, which is the elastic strain tensor, and another tensor, which is the plastic strain tensor. How is defined the elastic strain tensor? The equivalent to that in 3D. The elastic strains are the inverse constitutive equation, C minus 1 times sigma. So here we can use the inverse constitutive equation, the inverse Hooke's law that we have used in elastic materials. Okay? C is that elastic constitutive tensor that, for isotropic cases, depend on how many parameters? 2. Lambda mu or epsilon and nu, etc., etc. Okay? What holds for total value also holds when we differentiate. So the increment of epsilon is the increment of the elastic strains plus the increment of plastic strains, where the increment of elastic strains are C minus 1, this is constant, times the different increment of stresses. Okay? So this is the generalization of that. Straightforward generalization. Okay? Second, in 1D, we define first what we call the hardening variable, and we define a law, a relation of the increment of the plastic strains and the stresses. And if you look at your notes at the time, we see that the increment of uniaxial plastic strain was equal to d alpha, alpha being the new defined parameter that we call the hardening variable, times the sign of the stresses. Okay? And this d alpha turned out to be always positive. Well, what do we do here? Well, essentially the same. We define the tensor. Well, in fact, we change the name. To this incremental of alpha, d alpha, we call it lambda, and it's known as the plastic multiplier. It's always positive. It's in a scalar, and it's always positive, as it was alpha, positive. Second, this law is just generalized to that way. The increment of the plastic strains are equal to this lambda, this plastic multiplier, which has to be determined, times that. What is that? Well, for the term defining this, the equivalence of this, we define something which is a new function, a new material property, which is called the plastic potential function. We'll see that, for instance, in soil mechanics. That's the plastic potential function that depends on the material. That is part of our model. But is a potential, why? Because by differentiation of this function with respect to the stresses, we obtain what comes here that multiplies by lambda provide the plastic strains. It's like that. Okay? By the way, what would be the equivalent of the plastic potential function in 1D cases? Any of you know? Look, if we consider the Yell function that we define here, look, that function, what is the derivative of this with respect to the stresses? Is the derivative of the modulus of the stresses with respect to the stresses. What is the derivative of the modulus one function? Modulus of x with respect to x. Imagine that. When x is positive, is 1. And when x is negative, is minus 1. So it's the sign of sigma. So look, the derivative of f with respect to sigma is the sign of sigma. What do we have here? The sign of sigma. So that means that in 1D cases, the potential function is what we call the Yell function. So it can happen in 2D cases, in 3D cases. But this is more general. That could be the potential function, can be the Yell function, or it can be another one. That is a more general approach. Just keep this point in your mind. So now we define the Yell function. The Yell function in 1D was defined as the modulus of sigma minus the yield stress, the yield stress function. And in that case, we just do an equivalence. Instead of doing that, we put here a scalar function of the stresses. This is called the equivalent uniaxial stress. So in 1D cases, this phi of sigma is the modulus of sigma. In 3D cases, that is crucial. Definition of this defines different models of plasticity for different types of materials. We will go to that point. But the concept is the same. We define the traffic light function that is a scalar function of the stresses and the equivalent strains and the hardening variable, which is equal to the uniaxial equivalent stress, phi, minus the Yell function, the Yell stress, in such a way that this function is always either negative or equal to 0. It's never, never, never positive. It cannot be. We postulate that this function, it can be only negative or equal to 0. Okay, let's look now, whatever is that. This will define a function in the stress, in the high Westergaard stress field. A function that contains the origin, and if we consider, imagine that we just consider a fixed value of alpha. That's a function. The interior of that function, that is when this function is smaller than 0, defines the elastic domain. The surface of that function, that is when f is equal to 0, that defines the limit case, the elastoplastic state. And the exterior of this function cannot be achieved if we keep alpha constant. Okay? So that is the generalization of what we did about the traffic, what I termed the traffic light, the Yell function as a traffic light that says when the function is smaller than 0, that means that we are at the interior of this domain in the stress domain, and we call that state as elastic. This is anticipation of what's going to happen here, that the material is elastic. When we are just at the boundary, we can move and stay at the boundary. Okay? We can move around there. That's fact feasible. But then we are in a different regime, the elastoplastic regime. And if we want to go away from that, then we cannot keep alpha constant. We have to generate a variation of alpha, and so that domain increases in order to have larger stresses. Okay? So that again defines the elastic domain. Of course, there is an initial elastic domain, that surface. What happens when alpha is equal to 0? When we are for the virgin material, there is no elastoplastic strain. The material comes out from the factory with no generation of elastoplastic strain. Then, of course, that function takes a certain value, depending on the definition of that. But takes a certain value. There is an original elastic domain, which is the set of stresses such that function f specified for alpha equals 0 is smaller than 0. And on the other hand, when alpha increases, that domain expands, and then we have the elastic domain that is now different from the initial one, and we have an admissible stress space, which is made by the interior plus the boundary. So the elastic domain plus the elastoplastic domain. Okay? So this is a straightforward generalization of what we did in 1D cases. Okay? So, next step. That is maybe a little different of what we did, is a generalization of what we did in 2D cases. These are conditions to define when the point is a loading or in a loading. These conditions, in fact, are quite related to another completely different discipline, which is optimization. So these are conditions which mathematicians know very well, which are called the Karush-Kuhn-Tucker conditions for optimization. And they say that the lambda multiplier, the plastic multiplier, is greater or equal to 0. The L function is smaller or equal to 0. That's what we postulated here, by the way. But their product is always equal to 0. And in the limit case that f is equal to 0, lambda times the increment of f is equal to 0. These are what we call consistency conditions. Look, these, maybe through mathematical operations, allow computing for every value of the stress and alpha the plastic multiplier. I'm not going to explain that, okay? That's just a matter of mathematical operations. But let me explain something about what this means. This equation. Look, lambda times differential of f is equal to 0 whenever f is equal to 0. So f is equal to 0, that means that we are just at the boundary of the admissible stress space. Okay? Then what can happen here? It can happen three things. Like first, that next move is towards the interior. Next move is tangent to the boundary. Or next move tends to be towards the exterior. Okay? That's the thing. So that's related with that. Look, f is equal to 0. And differential of f is smaller than 0. What is this move? We are on the boundary and the increment of f is smaller than 0. So next value of f would be smaller than 0. So we are moving towards the interior of the elastic domain. So if that is different from 0, because it's smaller than 0 means strictly different than 0. What does this product say? If the product has to be equal to 0, and this is different from 0, then lambda is equal to 0. Okay? So if lambda equal to 0, the generated plastic strain, the increment of plastic strain, which is defined through that equation, is 0 too. So that means that in this situation, it's a situation in which the point was just at the boundary, it moves towards the interior, and the conclusion of that equation is that there is no generation of plastic strain. Okay? Second possibility, f equal to 0, but now differential of s is strictly equal to 0. Strictly equal to 0. Well, then that equation is fulfilled whatever the lambda value is. So in that case, lambda is equal to 0 or lambda is greater than 0 from that. Lambda cannot be smaller than 0 because that condition precludes that situation. For lambda equal to 0, then this rule also establishes that since lambda is now equal to 0, the generated elastoplastic strain is equal to 0. Okay? So that is a situation in which we are at the boundary, but now we move tangent to the boundary. So there is no change of alpha. That is what we call neutral loading. The first case, I maybe didn't mention that, I'm doing it now. That first case was called elastic unloading conditions. Okay? Elastic unloading conditions. The second case, that case, is elastoplastic neutral loading. So that means in terms of this graphic interpretation, that we are at the boundary and we remain at the boundary. We move on that boundary. And that means that we do not generate any plastic strain. Okay? And finally, the third situation is that lambda, differential of f equal to 0, lambda is greater than 0. What does that mean? That means that that product now, lambda is different from 0, there is generation of elastoplastic strain, and in consequence of this equation here, there is a generation of alpha. There is a generation of alpha, and then there is generation of plastic strain. So in terms of this geometric interpretation here, that means that we are here and the point moves towards the exterior. But look, by changing the value of alpha. In that equation, if we change alpha, then the size of the surface changes. So this surface expands, the elastic domain increases, and we have what we call hardening. The material hardens. As this surface expands, the size of the stresses that can be achieved by the material, even in 3D cases, is large. So we talk about hardening. Okay? So looking finally at this situation, there is another case that we haven't considered, which is f being equal to 0, so staying on the boundary, differential of f is greater than 0. That cannot happen. Differential of f is not greater than 0. Cannot be. So we can stay on the surface and go to the interior, on the surface and remain into the interior, on the surface and increasing the surface. But differential of f also being equal to 0. So being on the surface means that now the surface is dragging the point as it expands. Okay?